Hey everybody, this is Larry. This is me going Q4 of the bi-weekly contest one day. Find products of elements of big array. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. So this one was very hard for sure. I think this is actually a video where if you watch me solve it live, at least the first part of I took an hour or so, but a lot of the second half was just off by once. But I think the first half you can kind of see me. If you watch it fast forward or in a faster speed, you could kind of see me struggle with it. And the first thing that I did is I kind of, the first observation that I noticed is that, of course, these are just the expansion of the binary bits of the nth number, right? For example, yeah. So yeah, this is okay. Let me just write it down here. So like, for example, the first number is just 1, this is just 2, this is 3, I'm just going to write 3 so that it looks like this. And then this is 4, this is 5, this is 6, this is 7, and and this is 8, right? And here you can kind of see that it is obvious that you have 1, 2, right? And so I asked the second observation that I would point out. Oh yeah, and this is obviously the binary representation of that number, right? So the second thing I would point out is that queries the numbers can go up to 10 to the 15. So that means that we have to have a fast way of calculating what the number is, right? Okay. So the idea that I was playing around with this was with binary search. Let's say so the first thing I did was that, okay, let's say we have, and the binary search is pretty straightforward, right? If you have some components, which is to say, let's say, we go 7. How many numbers are there 7 or less, right? Before 7 and less. And that's the idea that I'm trying to get. And that's the binary search, is that, okay, if the queries are pretty big, let's say this is, I don't know, 100 million or whatever, I didn't count it, right? Then now we can binary search to get that very quickly, because then we know that, okay, let's say f of 100 is equal to, I don't know, some number, and then f of 1,000 is equal to, some number more, and so forth, right? I don't know if this explanation is even good, but basically you binary search for the number. Let me write that out then. Binary search for the real number pre-expansion by getting the count or the sum of counts of all previous numbers, right? So for example, here you can say that 1 returns 1, 2 returns 2 numbers, 3 returns 4 numbers, 4 returns 5 numbers, 5 returns 7 numbers, 6 returns 9 numbers, and 7 returns 12 numbers, right? So, and as you can see, this is monotonically increasing, and because this is monotonically increasing, we can do a binary search, right? Assuming that if we can get, if we can have a function f such that f of x is equal to some number t for, I don't know, right? Where y is the the sum of the count of all previous numbers, right? So then now we have this function, we can binary search. So now we reduce this problem to binary searching for this, right? And the idea that it took me a while. I didn't actually, I have done a similar problem, not this problem, before, but it didn't really occur to me until like a little bit deeper. So what I did is I have a notepad here, and I kind of drew it out, right? So okay, so 1, what does 1 look like? This is 1, right? The other way, whoops. This is 1, this is 2, this is 3, oops. Maybe I didn't need that many prefix zeros, but this is 4, this is 5, this is, I'm too late, it's committed. This is 6, this is 7, this is 8, and this is 9. I mean, there are definitely different ways of doing it, by the way. but that's just the way that I remember it from another problem that I've done not that long ago, maybe it was like a year ago. But yeah, as you can see from the obvious idea, the first obvious pattern is that the 1 bit is to make it consistent. Actually, I should add in 0, right? So the 1 bit is going to be like the first bit is going to be go from 0 1 0 1. So if we have a digit a number x, half of it is going to be half the numbers are going to be ones, right? I think that's pretty straightforward, right? To understand. Of course, we have to deal with, like, rounding and stuff like that, but yeah. So given a certain x, half the number. But what about the 2-digit? Well, the 2-digit, and this when I started writing this out, I'm like, oh, I do remember this. So this part I did skip a little bit, if you will. But the idea is that, okay, that means that for every 4 parts, right? Like if I'm looking at only the second digit, the 2-bit, every 4 parts you have 2 zeros and then 2 ones. 2 zeros, 2 ones, right? So 2 zeros, 2 ones. So that means that, again, half the numbers are going to be ones, but it's distributed a little bit differently, right? It means that, yeah, for every 4 numbers, there will be 2 zeros and 2 ones, right? Okay. So then, is that a pattern? Well, we look at the next one, the 4-bit, right? And then now you have, for every 8 numbers, there will be 4 zeros and 4 ones, right? And then ... really, to be honest, right? So then now here, now we can figure it out. Now we have, an idea. And this is basically how I started doing this, right? And that's really the core of the idea. So this is counting the number of total bits on, this actually comment is terrible, but number of total bits under x, right? So so now we count the number of ones. How many ones are there for an x? Well, because I did an x increase by 1 because it initially didn't count this 0-bit. But yeah, so that's that. And then I just kind of expand this to 64 bits, right? Just have a frequency table. And actually, it turns out that you can actually do this a little bit differently, but I'll go over that maybe in a sec. But yeah, But yeah, we just count all of them. And then the number of ones, and this is the number of parts. Why did I write it this way? Oh, I mean, I did it because of the number of bits. But okay, so this is the bit that we care about, right? So maybe you could write this as actually 2 to the power of j, right? So for example, if the 1 bit, if p is equal to the 1 bit, then that means that the total part, which is for every part, for every d number, let me write it here, right? Oops. For every d number, and I'm doing this to match my variables, there will be, p zeros and p ones, right? And of course, so now the math is actually a little bit easier, right? Because whole is just the number of whole parts, right? So for example, if you're on the 1-bit, then that means that the number of 0, 1 pairing, you can maybe think of it as pairings, right? So then now if j is 2 or j is 1, so p is equal to 2, then for every 4 numbers, so now whole means that for every 4, how many groups of 4 numbers are there, right? And then leftover is just the numbers that are left over. And because we want to count the number of ones, we skip the first p zeros, and that's where we get this from, right? So leftover is x mod d, but then minus p, and it was less than 0, then we don't have any, right? So yeah, and then this is the number of bits under x, and that's what we get. Okay, so then now after that we have a binary search. So then now given x, so given we want the x number, we just do a binary search, which is that, while left is equal to right, we do a binary search if the sum of all these, and that's just the total number of bits, which is the sum of this array. If the total number of all the bits is less than 6, then we binary search. It goes higher. Otherwise, we can make it smaller and try for it because we have enough. And that's pretty much the idea. And then so for every S and E, which I both start and end, that's what I kind of in my head. And the mod, we calculate the arrays with the arrays with leftovers, right? So here, given S, which is the input, and I did this, I think I count this off by 1 in the other way. That's why I have this S to E plus 1 instead of the normal E S minus 1 over E minus 1. And the reason why we can do it this way is just prefix sum, right? Because then now you could say to get a range from 1 to 3 is just equal to the range from 0 to 1, from 0 to 3 minus the range from 0 to 0, because we want to include the 1 and so forth. This idea I'm not going to go into too deeply because this comes up a lot, so you should know about this idea. So then now we get the left parts and the right parts, right? And here we have this. So this is a little bit different. So here we binary search to get the number, and then nums of p is going to be this coordinate that is just the distribution, right? So because here this function returns the distribution of the things, right? Like how many 1s, how many 2s, how many 4s, and so forth. So this is what this returns. So this is what this returns. And then we just want to count the number of bits that we have. And then the leftover is just the number of leftover bits that we have left over, right? Because if you look at this pattern, let's say we want to be at this digit, right? Or maybe I'll just look at here, I don't know why. So let's say we have at 7 and we want to look at this digit. Well, then that means that we just have to calculate how many 6 are there. We subtract it out, and then the leftovers is just going to be 2. And of course, it is increasing, right, in the number of 7. So then this just means that we want to get the leftover two numbers from 7. So that's basically what this is saying. And leftover is x minus the sum of the number of bits, right? Because x is just, the number that we care about. And then here we just get the first leftover number of bits in a greedy, small to large kind of way, right? So leftover goes to 0, we're Gucci. And then we just return number p, which is the array that counts all these things. And then we get it for the right side, we get it for the left side, we subtract from the right to the left. And then we just find the answer by calculating it, right? Because this is, because basically for here, and maybe write this as 2 to the power of I, right? And maybe you even mod that, or you could write, maybe this is fine. Right, so 2 to the power of I, and we have f of I of these, so we want to take this to the power of that, and then we take a mod. There's actually another cool way that that you could combine these, but this is the core idea. I want to get this idea off fast. So what's the complexity here, right? Well, so go with leftovers. So they're Q queries, right? All of Q queries, obviously. Go with leftover. This calls a binary search. This is all of number of. So this one, right? This does an all of bits loop, right? Binary search is the number of bits. But it calls this go function, and this go function is just all of number of bits as well, right? Because it just does an O of B loop. O of B loop. So this is all of, in total, this function is going to be O of B squared, where B is the number of bits, in this case 64. And so this is O of B squared, this is O of B, this is also O of B, and this is O of B. So this is dominated by this thing, which is O of B squared. And as a result, this is going to be all of Q queries, all of B squared functions. So that means that this is actually going to be O of Q times B squared time, right? And Q is 500, I want to say. I think they said. And B squared, well, B I put 64. So, that's 64 squared times Q. And that's pretty much it. For space, I think I just do O of B space in a lot of places. I don't really do anything more. But I think one thing that is cute that I saw someone mentioning is by yeah, the thing that I would say is, yeah, it turns out that I didn't need this sub array, I think. I mean, I think it makes this part a little bit easier, but it's not even because you can just count, because you can keep track of not the entire array, so you could keep track of number of twos. For example, one has 0 twos, so one doesn't affect the result at all, actually. But well, it does for the counting. But it has 2 as 1 2, 4 as 2 twos, and the reason why if you do it that way is that then it makes this a little bit easier and just cleaner. So yeah, that's all I have for this one. Let me go over the code real quickly again. This is the O of Q part. We go with leftovers, and go with leftovers. We do a binary search to find the number, and then we calculate the leftover to get the number of bits. And so yeah, so this is the go with leftovers. Go B is go binary search. Gob. But yeah, this is just a binary search on number of bits. And yeah, this is the binary search code, and this is the count the sum of bits under Xcode, right? Yeah, that's all I have for this one. Let me know what you think. Thanks for watching, and yeah, you can watch me solve it live during the contest next. Remember, I do struggle in the beginning. I do play around with a lot of stuff, and you do see it on video, I think, a lot of it. So let me know what you think, and yeah. Boop. No time limit, please. Just have to check for that one. Right, wow, no one got this one yet, so I'm a little bit behind, but not too far, hopefully. I don't know why I even check here. It doesn't even update. Shortest sorted array of powers of 2 sum up to X. Okay. Big number. Power away from every. Wait, what? Oh. So this is just binary digits thing. Is there a mod? There's still a mod, but no, mod's fine. Oh, you're given mod. Okay. That is indeed a tricky one to read, for sure. Code is only 500. That's interesting. Can you do the prefix thing? I don't know. So 3. They don't even tell you that this is 0 indexed, even though they should. Because 1 to 3 is these chunks, so that's 0 indexed. Alright, fine. So 10 to the 15, okay. Oh, no one's gotten it? Don't really have any ideas off my head. Multiply. So the minus there. What does that mean? So half the numbers are going to be 1, the other half is going to be 2. Is that even true? No, is that even true? BRB, I'm going to use the restroom real quick. But I'm going to bring my notepad with me so I could do some playing around with. Yeah, I don't know. Definitely need to play around with more. Okay, fine. 3, 4, 5, 6, 7, 8. I mean, the binary part is pretty obvious, but then it's the number of bits. Just even counting the number of bits is tricky. I'm glad I did the other 3 kind of fast. Not too fast, but reasonably fast. Because I don't know that many people are going to get this one. Man. So then it's just the number. What's it called? Bit count. Is it bit count? I forget what it's called. So the new bit count is the number that's going to be before the whatever. Then what about the pattern before? So we could, so it's something about getting the most significant bit, right? Because then it's just counting the number of 1s and 2s and 4s and 8s, possibly in between them, right? Oops. Okay, so I think that's a good approach. The number of 1s. And maybe we can even do a binary search on. Can we do a binary search on this sequence? I don't know. Alright, so then what's the prefix sum here? Let's see. Nope. This is what I want. Does this give me any pattern? Don't think so. To be honest. Multiple times. Well, if you could get the number of whatever, then you get the number of whatever, right? So 31, what does this mean? So let's say we go up to 8, what does that mean? Right? Okay. Too hard to watch. Is this always true? I guess so, huh? Now we have something. Maybe, I don't know, that's true. Okay, but I mean, let's just skip the number of bits at least, maybe. But how did I get there before that? Bit by bit? I mean, this is going to be very annoying, but it's doable. How many ones are there? So given the number 30, how many ones are there? Why are there 15? Half of them are ones. Okay, how many twos are there? Why is there 15? It's the sum of all the things, right? 29, 28, 27, 27 having 14 is... Okay, so the number of ones is definitely just divided by 2, right? Let me take a note, I guess. That part is easy. What about the number of 2's? Is that we do it by 2? Oh, I see. It's going to be 2 every 4, right? How do you get 11 then? Oh, yeah, okay. It was 22. 2 every 4, but this is the first one, so you get next one next. Okay, fine. So we could do a binary search, and then we just count all this. Okay, we could solve this. Yeah, just so, because we've done it before. And 4 every 8 and so forth. Okay, okay. A binary search. So let's just say we do this first. Right? So then now we count the number of things. So then now every, okay, yeah, I do remember doing this, or this part. Okay. Yeah, okay, okay. So then now we have, it's more than 32, right? Because it's 10 to the 15, which is actually very weird. But, okay. Well, maybe it's, I mean, it's fine, it's just very weird. Let's go B for bits. Whatever, okay, I mean, I didn't need to fix that. Okay, so then now, for J, it is going to be okay, so 1 to the J is going to be the half, right? So D is equal to this, and you want it times 2. And then whole is going to be D or X divided by D. That's the number of whole pieces. And then leftover is going to be X mod D, right? And then F of J is just going to be number of whole pieces times J, 1 times J. Okay, so P for pi, I don't even know why. So then, each part will have 1, yep, okay, fine. And then plus, so leftover is going to be max of leftover minus P for zeros and 0, right? Okay. Whatever. I mean, okay, yeah. Yeah, I mean, we could fix it later. still have this thing, which is fine. 1, 3, and 7. Right. What? I don't print it. Oh yeah. Wait. Why don't I print it? Okay, we don't need to print this then. Why doesn't this do anything? Oh, because I return here. I am the dumbo. Okay, 0 and 2. Is that even true? I don't think that's true. Right. 1. It's not inclusive, is that right? Let's do this. So 1 should be 1 and 3 should be 4. Am I getting that right? 0 and 2 is definitely not right. One, I have 1, 1, 0, 1 P. Whole is going to be 0, that's fine. X is 1, 1 left over is going to have per 2, right? 1 should be 1 whole, so okay, so I think I'm just off by 1. Right? Am I only off by 1? If we have 2, what happens if we have 2? 2, we go, this is 2, this is 4, whole is going to be, for 2, did I mess this up? 0, 0, 2, 2, yeah, oh, 0, 0, 1, 1, right? So whole is going to be, for 2, because 2 is the third number, okay, fine. 1, 4, okay, we're on the right track with what we wrote. What is the other queries? 2, 5. The way that I'm doing this is really even. 2, 5 is 2, 7, 2, 7, and then 7, 7 is, or 7 is just lookup 12. Okay, so I think we're doing okay on this thing. I didn't really think about it this way yet, but 3 people got it, very smart people. Not surprised that someone's got it. If I could figure out halfway there, then someone's got it. Okay. And then now we binary search on, oh, the queries are actually, I mean, I'm doing it wrong. It's not the 7th, because this is not the 7th number, it is the 7th thing, right? So then now we have to figure out the first number that goes into it. So maybe go B for go binary, I don't know, gob. For X, right? Oh, this my part is because it's not a prime. This may give us trouble in the way that I was thinking about it with prefix sum. No, but that's fine because we can subtract it out the way that we did this. Maybe. Yeah, okay. Well, it's still not easy, but it's doable. Okay, we have an hour left. Let's see. Okay, so binary search. 10 to the 15. How fast does this grow? I don't know. Let's just do 10 to the 15 then. Oops. What did I click on? Hopefully I didn't submit by accident. That has happened before. Let's do my okay. Just keep it the same. Why not? would I want this exactly to be? The number that contains X. Okay, this is terrible writing, but okay, fine. Commit is less if this is less than or equal to X, we want to try as well. With X we probably just got it, but if it's less than X, then we want to try a bigger number. Right, so now we can see that 1, 3, this is part of 1, and the third number is it part of 3? Don't know. The third number is part of 3, 1 and 2. Okay, so at least that's right, maybe. Equals space. Yeah, okay. 2, 5. 2 is 2, right? And is this 5? No, this is, wait. No, I okay, 5, but this is 4. This is 4, so that's good. Okay, so we got the numbers backwards, which is good. Okay, so now we have okay. Right. Maybe that's a little bit too weird, but okay, fine. And then now we have to do the extra X part, right? I wonder if I should cache this. I don't even know if that helps, but okay, focus. You could do this. It's not that bad. Okay. How do we get X extend into a number? X instead into a number, right? So okay, oh yeah, then that's just the first bits, right? So that's not so bad. Okay, fine. So then now we have left is equal to right is equal to and then left over is equal to S minus left. No, that's not right. Well, left is the, oh yeah, because this gives me this, but now we want actually go to probably and then now it is just the prefix, right? So we can just do a loop. Yeah. Okay, left sum is equal to this. And then, oh. Yeah, okay. Maybe this is like P for parts. so then now we have left. Okay. This is inclusive. Yeah, okay. So then now. Well, no, we want s minus 1, right? Queries could be 0, which is awkward. For sure. Because we definitely do want to remove 1 digit from the leftover to be not included in this thing, right? So, okay. I don't know if this messed me up, to be honest. It may. Because everything assumes 0 indexed. But, alright. Okay, then it's just right p minus left p, right? In an array kind of way. And then now we have to care about the leftovers. The leftovers is just 1 number, right? So then it's just the first leftover bits, right? Yeah, it should be okay. So then now, so then it's left and the leftover bits. I don't want to do, yeah, okay, I mean, I want to do this. I should remove this just in case. But, I mean, it'll give me a wrong answer anyway, but maybe that's fine, I don't know. But yeah, am I returning the right things? If this returns the first, if it is exactly the same, we make it smaller and include it, okay. So this returns the first number that's bigger than it. Is that true? I don't know if that's true. Alright, let's just skip this part for now, and I actually want to do 1, 2, 3, 4, 5, 6, 7, 8. Let's look at 8 and what I print. Oh, whoops. That's not good. Okay, well. Why did oh, because it's 7 digit. 1, 2, 3, 4, 5, 6, 7. It's gonna be 4, which is part 5. That's right. It is part of it, but we actually. What is the leftover? Yeah, that's what I feared. That's not bad though. This minus 1 is what I want. Okay. Because now it's 2 digits of the 5th number. which is what I want, right? Maybe. Two digits of the left number. Okay, we're doing left. Well, this is left. I think maybe this is actually more accurately like this. And then now we can do this assertion again, maybe. 5 is that should be true though, otherwise it's going to give me errors. That's why I'm doing it. Alright. 1 over. Oh, it should be less than equal to. I think that's fine then, maybe. Double check. Okay, that looks good then. Okay. So then now. Okay, so then now on the left side, then we want to subtract 1, right? Okay, so then now yeah, maybe this could be a helper, I don't know. Right, and then now we have f, so then it's just for I in range in f. Is it? No, f is in the way. Okay, fine. Okay. It's not mod, it's M from okay, fine. I'm really worried about off by ones, but I think this is a good start. 6. Well, I mean, this would be a good start if I got it correctly. Anyway, okay. Why do I have 6 and 0? Okay, well. Okay, so there's 2. That's definitely wrong. Right is, and left is going to be 0, 0. Okay, so there's 2 1s and 2 2s on 3. That's, well, it's missing the, it has an extra 1. Though that shouldn't change the results. It shouldn't give me 6, right? So where does 6 comes from? Left P doesn't make sense. Okay. Oh, what the? I did too much there. Okay, so 4 makes good now. The other two, not so much, maybe. Yeah, 2 to 5. Is this even right? I think this is actually wrong. We're just maybe a little bit lucky. Two. Yeah, I think this is just lucky. We're wrong here. Okay. Let's do this before we do the leftover stuff. Before the leftover stuff, it is 1 1, which is also wrong. What is left P? Left P is nothing. Right P is 1 1. Oh, because it does not include the 1 and 2. I guess that's fine. And then let's make sure left, right, 0 and 3. Yep. And 1. Oh, 1 is not right. 1 is right in the number of bits, but not the takeovers, leftovers. I mean. Now it has to be that because then now. That's weird. Okay, let's look at it again. I mean, it's the one is kind of wrong, right? Yi, we want 4, but this should actually. White P, no, white P is right, so it only has 2 numbers, so okay, I think I got it. I think this is a little bit awkward, but I think this is right. Okay, maybe not. We could 2 numbers, 1, 3, but then the 4th number, right? Yeah, so this is the 4th number. Which is part of the 3, which actually is right. The 2nd number of the. Now the server's having issues. Okay. So F is going to be this, etc. Today. I guess that's relatively true. No, that's not true, is it? White P is this. Oh, that's right. Left P is this. Okay, that's actually right. Okay, I'm just being dumb again. Okay, so then why is this wrong? I'm gonna click on submit by accident at some point. 1 and 2. Oh, so left takeover is the wrong one. because we want 2, but then we want one of the first number, which is true. Then one of the first number is this one. Bit count is, am I right? I don't, this feels very wrong though. Like I just do it this way. It's not even right anyway, so okay, fine. We're so close with half an hour to debug this, but the zero and the indexing is getting me again. I'm just not practiced enough for this. So 1, 2, 5, 6, 7, 8, 9. Okay, I'm curious. Oh yeah, okay, that makes sense. No, this is on the left side, that's why it's a little bit awkward. And because we manipulate this. Yeah, okay, fine. 8. Is this 8? Well, this is off by 1, isn't it? Off by the leftover. So that's right. Because we want this. No, the 7 and the 8 giving the same thing is probably not right. Oh no, I reversed the order. Okay, so this is 10. That's actually really weird then. Oh yeah, that's right then. This is 7 and this is 8 and this is 7 is also very weird, but this adds 2 numbers. So you have to do this. Okay. What is this? Okay, yeah. This is prefix, and no, this is just to calculate, right? So this is the number, and then this is the prefix, the number. Right, and then now for if Okay, so then now we can just go why did I name this so long? Okay. Okay. I mean, we don't even need a second thing, but that's fine. So this difference is 0, 0 is 4, right? So then, wait, what is f? Okay, so the third example is going to be 4. 4 mod 4 is 0, but am I off by 1? I guess so. What is the seventh number? Oh, 7, 7, okay. 7, 1, 3, 4, 5, 6, 7 is actually 2. Huh. So that's where this is definitely wrong. This seventh number. Okay, at least we can. Okay, we're trying to get the seventh number. Right. One, 2, 3, 4, 6, 7. Wait, is it? Oh no, this is the seventh number because it's 0 indexed. So then now this would have two 4s. So 332 is the right answer. But we have this and 332. I'll just go leftover. So we have 7, we have 2 numbers left over. So we're off by 1 is why. On the number, and this would be, what would this number be? 7 is 5, right? Is this a 5? 0, 1, 2, 3, 4. Oh, 1, 2, 3, 4, 5. So no, that's why. The binary search is off by 1, isn't it? Because this is returning 5. Okay. And it should return maybe 6. Maybe, I don't know. Yeah, no, this should return 6. we want this to return 6. So why is it not? If should get this, but I'm so dumb today. 7 9 0 1 2 3 4 5 6 7. I see. So we want the 8th number, but yeah. Okay, so maybe I am just off by 1 here. So now 7 6, but then now this is all wrong. So I don't know. All right, why is this wrong? Okay, so 1. Oh, this is wrong. Oh, we didn't do the leftovers yet. Okay, let's do it here. Okay, so this is right, and then 4 is 3 4, so this 2 2, right? 2 2. So then, why is this wrong? 2 1. Yeah, this is should be right. Right. 4 times 1 over 7. Why am I getting 5? Huh? Tell me why? Two twos is 4, right? What? Am I debugging everything? I'm just like so dumb today. 5 5. Oh, whoops. Oh, 1. Oh, I am dumb. I am dumb. Okay, that's not bad. This is not a motive. I don't know how I got this off for so long. Alright, that's not Gucci, but this is if. Alright, a little bit closer, but still wrong. That's fine. I mean, this is just really plain wrong. I don't know what I was doing. Yeah, I don't know what I was doing there. Okay, 20 minutes. Focus. 7 7 is. Oh, because it we took. Well, no, the 7 7 is just wrong. But why? Because this should be y plus 1, so this should be 8, right? So 8 gives me same as 7, 0 and 1, because we had, I thought I took care of the leftovers. How is this right? Leftovers is 1 for 1. What am I off by 1 by? 2 leftovers on 3, okay. The 2 leftovers on 7, right? So, oh wait, 5 should be a 6, right? That's what we keep on saying. Why is this a 5? Oh, wrong, wrong, wrong. 0, 1, 2, 3, 4, 5, 6, 7. And this is part of the 6, and it should have 1 on the 6, not 2 on the 7. And also this has a leftover, so I think that's also an issue. So 7 is going to be 5. I'm like doing something weird with the off by ones. Because then next 6, 7, this is actually right for the first 7. But then I'm not, this one is not right or something. Something is, okay, so 8 is wrong. I think that's why. Okay, 8 is now right. For this one, it is properly the first number in 6. But then now this is wrong again. Right, which is now Gucci. Why is that wrong again? This is 2 to 5. 2, 5. What's that? 2 times 4 is 8. 8 mod 3 is 2. Wait, this is right? 2. Oh, this is in this is wrong. This is not the number of count. This is POW, right? Okay. Wow, I'm just like, nope, the other way around. Okay, this was actually a great bug. Or great example for a bug. Okay, I don't know if the last one's right though, but do I want to YOLO it? 8 to 10. 0, 1, 2, 3, 4, 5, 6, 7, 8. 8, 9, 10. I mean, yeah, that's gonna be even. But let's try a bigger mod then, right? Then was it 8 to 10? 0, 8, 2, 0, 1, 4, 5, 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is 8, and then 9 and 10 is going to be 2. Okay. Oh, that's still an output. Let me make sure I don't output limit exceeded. Let's YOLO. Probably still off by 1 somewhere, but at least we got close. That's all you can hope for. Oh, I forgot. Ooh, actually, I messed up here. This should have been a modded. Maybe that's a little bit faster. This should be faster no matter what. But it's only 64 numbers, so maybe not that much faster or slower or whatever. Whew, that was a tough one for sure. I'm gonna just check the timing. 8 seconds is pretty tight. Let's make some optimizations before I call it finished. Because you know. Do I want to cache any of this? Definitely do not want to cache go, because we do manipulate it. This is actually very close, to be honest. I'm not happy about it with the timing. Can I cache anything that's easy? I mean, if I rewrote this as recursive, then I can, but that's just tough. And even though, actually, I don't know if that's true. I may have lied on that one. Oh well, I didn't get in the top 25. I mean, this was a weird. Wow, a lot of people got this. It turns out. I thought. Oh, I didn't refresh this page. 59. I guess that's a good, reasonable amount. I mean, I definitely could have been faster. I was just debugging off by once for so long. And also, I was also just using the wrong formula because I got confused about a bunch of things. So I don't know. Don't know that. And I got that formula wrong twice. Can I optimize that much more? I don't even know that I can, to be honest. And I don't even need this anymore, I suppose. I was wondering why I needed that, but then it's because I did something really funky. Tempting to submit to some. Definitely not a sort. Go. Maybe this function if I don't do it as a function. I don't know if this makes it that much faster. Let's give it a spin. It's free now anyway. Yeah, not that much faster. A little bit slower even. Oh, because I removed the if statement. Yeah. I guess this part. Oops. I mean, that gets executed a lot, so I don't know. I would like to get it like just a bit tighter. To be honest. I don't know. Oh, okay. See, the reason why is that this is inside like the part that we call the most, so that's probably why. I don't know that I could see this doing much more. I can try this. How much memory do we use? It doesn't say. Okay, fine. I don't think this does anything though, to be honest. Actually, I think this messes things up because we cache the memory address instead of the thing, so it's even worse. I think I actually thought about that. I think we just need to put it here though, so I think that's fine. Yeah, maybe give us submit real quick. Could give us the wrong answer because maybe I cached something out. That is silly though. I don't know that just depends on the input, so I think that's just like though we do explicitly call this as part of this, I think, so this definitely saves it a little bit of time, but and maybe there's some duplication in the mid, but that's just like a input sensitive thing. I think that's not a real optimization, like a very minor one if it's a real one, but it's not like a real one, I would say. I was hoping I did a little bit better, but apparently a lot of people saw like right before I submitted it or something. Oh no, well, with wrong answers, so they submitted like earlier. So maybe I'm even a little bit behind. But only 48 up to this point. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this contest, this problem, and everything in between. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.